Hello, everyone. We are going to do property of power series today. So we're going to combine power series by addition and or subtraction. We're going to create a new power series by multiplication by a power of the variable or constant, or by substitution, multiply two power series together, and then differentiate and integrate power series term by term. Okay, so any questions about this? Okay. So the first thing we're going to do is define the power series we are going to use. So these power series are going to be this series. A of X is one power series and B of X is another power series, and they both are convergent on the same interval. So they may each have a different interval of convergence, but you're going to have to take the smallest common interval that they are both convergent on. Okay, so addition and subtraction of power series. So let's look at this. So in order to add or sum a power series, actually that I could make that addition or subtraction. Yay. I can make addition or subtraction. Aha. Okay, so let's look at two different power series and see what happens when we add them together. All right. All right, so my pen seems like it's going to act crazy for a bit, so maybe I'll type this in, because that will be better. Okay. So I have the sum n equals 0 to infinity of x to the n. That's one power series. And then we're going to have another power series. N equals, whoops. N equals, oh, now it won't let me do that. I had the same problem last time. This is also n equals 0 to infinity of minus 1 to the n x to the 2n over n factorial. No idea why this is not working. I'm just having a moment. And again, summation. So this is going to be a of x. And that's going to be x to the n. And then b of x is the sum n equals 0 to infinity of minus 1 to the n x to 2n over n factorial. All right, so we can add these together and get a of x plus b of x. Is the sum n equals 0 to infinity of x to the n plus a minus 1 to the n x to the 2n.
Because it's like hashtag.
I don't know what.
Call me fucking short. One more.
Well, that's going to be cute on this video. So the first term is going to be 1 plus, and then the second term is going to be 1 as well. Then the next term is going to be x, and then I'm going to get minus x squared, and that's it, minus x squared. And the next term,
Don't use me. Don't use me for your prank.
Danielson, please. I'm discombobulated now. Okay, this is, where am I? X squared. And then this is going to be x to the 4th over 2 factorial. And then the next term would be x cubed. And it's going to be minus x to the 6th over 3 factorial plus dot, dot, dot. Okay, so as you can see, we'll be able to combine terms in the end. So it will also be a power series of x powers. Okay, any questions about that? Let's do multiplication of power series. Now I'm actually going to use those same power series I just used. Okay. So if I want to multiply these two power series, I think I actually, yep, I have that same thing. Here we go. So I'm going to do the example on this one. This is what I'm going to do. I will use that one. But if you're doing this, this looks like A0 plus A1 plus A2 plus dot, dot, dot times B0 plus B1 plus B2 plus dot, dot, dot. Your first term is A0 times B0. Your second term will be A1 times B0 plus A0 times B1. So it's kind of like we're foiling it, but we're foiling it with infinitely many terms. So we can only take a few of them at a time. Your next term is going to be A2 times B0, plus you're going to get A1 times B1, and then you're going to get A0 times B2. So if you notice, each time I increase where the A's start, and I start with the decrease of the B. So we call this C1. This term is C2. This term is C3. So we get another series when we multiply it out. And this turns out to be the sum n equals 0 to infinity of Cn, where each Cn itself is a sum. So it's the sum k equals 0 to n of ak times bk minus 1. Why do I feel like bn minus k? That's right. This is wrong. This is bn minus k. Okay, so that's right. Okay, all right, so let's do that. So we're going to get this example. Okay. All right, so we already know what the first series looks like. So the first series is 1 plus x squared plus x cubed plus dot dot dot. And the second series looks like 1 minus x squared plus x to the fourth over 2 factorial minus x to the 6 over 3 factorial plus dot dot dot. Okay, so the sum, we multiply the first term and the first term, our C0 is just A naught B naught. So that's 1 times 1. That's 1. Our C1 is A1 B naught plus A naught B1. So this one here is just A naught, A1, A2, A3. This is B naught, B1, B2, B3. Okay, so we're going to get A1 times B naught. So that's x times 1. Plus we're going to get A naught, which is 1, times B1, which is negative x squared. So we get negative x squared plus x is our next term. C2, A2 B naught plus A1 B1 plus A naught B2. So A2 is x squared times B naught, that's 1, plus A1 is x times B1 is negative x squared, plus A naught is 1, and then B2 is x to the fourth over 2 factorial. Okay, so now we can say that our series, when we multiply it, and we keep going. So therefore, this series that we have, and you can only do it term by term, and it takes forever. So if it's asks you for the if it asks you for the sum of the product of a series, they're only going to ask for like the first 3 terms. So this is going to be 1 plus negative x squared plus x plus x squared minus x cubed plus x to the fourth over 2 factorial plus dot dot dot. Okay, any questions about that? So that's what you're going to have to do.
Dr. What?
Yes.
So the answer is that we'll just have to write out every term for the first
They'll ask, you would only have to do
9.
the first 3 terms.
Okay.
Otherwise, because they take a long time to calculate. You see what I did? I didn't even get to do C3, which would be A3 B naught plus A2 B1 plus A1 B2 plus A naught B3. So the next one has 4 terms. So the series to compute the product takes a long time. All right, differentiation of power series is actually rather easy. Again, I'll post these notes for you guys so you can fill in any gaps that you may have. Because I have stuff already pre-written out. So, all right, so I'll give you a minute to copy this down. Differentiation of power series. We assume we have a function represented by a power series and that it converges on a particular interval. Then in order to find the derivative of the function, we can actually differentiate the power series. So we have Cn that stays there, but x minus x naught to the n differentiates by bringing the n down and getting x minus x naught to the n minus 1. Notice I started n equals 1 and not n equals 0 because n equals 0 wouldn't make sense. Okay, so then I do the sum n equals 1 to infinity. Now I'm differentiating again, so the x to the n minus 1 comes down and I get x to the n minus 2. And I can do this, I can find the third derivative, the fourth derivative, but I can use this to find power series for other functions. Here's a problem. Find power series expansion for the function f of x equal to 1 over 1 minus x squared. That's the wrong one. That's not the one I want. Nope, I don't want that one. I want 1 over 1 minus x squared. That's what I want. Okay. All right, so I need to find the power series for that. All right, so we only know certain ones, right? We already know the power series. So we know the power series if we have f of x equal to 1 over 1 minus x. We already know that that one is the sum n equals 0 to infinity of x to the n. Okay, and we know this converges only when the absolute value of x is strictly less than 1. Okay, so we do know that power series. Well, we also know this other thing, that oh, let me call this G. We'll call that G. So we know also that G, if you take f prime of x, you get minus G prime of x. All right, so let's see that. So f of x is 1 over 1 minus x. So f prime of x is minus 1 over 1 minus x quantity squared. And when we differentiate it. So that is just minus G of x. All right. So therefore, G of, don't want a prime in here. So G of x is simply negative f prime of x. Does everybody see that? Since G of x is literally the derivative of f prime without the negative. All right, so therefore the power series of G of x says differentiate the power series of f of x. So that says G of x, which is negative f prime of x, is simply the sum n equals 1 to infinity of nx to the n minus 1. So that's the power series for that, and I need a negative in there because I'm missing it. Negative. So therefore g of x is minus this. When n is 1, I'm going to get 1, and then I'm going to get 2x, and then I'm going to get 3x squared, and then I'm going to get 4x cubed, etc. So therefore, I now know that g of x equaling 1 over 1 minus x squared is simply equal to the sum minus the sum n equals 0 to infinity of, oh, n doesn't start at 0, it starts at 1 to infinity of nx to the n minus 1. There. So I found the power series for another function just from knowing the power series of the one we already know.
It increases your heart rate variability.
Any questions about that? All righty, let's do integration. Okay, we can integrate power series as the same way we can differentiate them. So integration of power series, we can assume f of x is equal to this series, it converges. Then the integral of f of x simply means integrate those terms inside. So you just make it x minus x naught to the n plus 1 over n plus 1. The only difference is this one continues to start at 0, and there's an arbitrary constant that comes along with this function. Okay, any questions about that? Fine. Power series for g of x equal to the natural log of 1 minus x. How would I go about doing that? And we can only use what's on the paper, what we've done. We can only use what we've done here. Okay. All right, so what's the derivative of g? So g prime of x. What's the derivative of g? Hello? Anybody there? How do you take the derivative of that?
Is it -1?
True.
over what's in the parentheses.
There's like slight differences, but like it's all the same.
That's
Okay,
right.
that's right.
Oh,
That's right. Okay. But we know the power series for this, don't we? This is minus the sum n equals 0 to infinity of x to the n. We already know what this piece, that piece right there is equal to this piece. We know that. All right, again, the absolute value of x has to be less than 1 for this. So in order to get g, I just need to integrate that. So therefore, g of x is simply going to be minus the integral well, g of x is the integral, let's say, of g prime of x plus the almighty constant. Right, so our g of x is simply going to be minus the sum n equals 0 to infinity. Did that last time, I didn't mean to do that. And then I'm going to get x. Let me do a fraction real quick. Now I'm going to get x to the n plus 1 over n plus 1. Because that's the integral. All right, very good with that. So g of x we know we're going to have a constant. That's the arbitrary constant. But then when I integrate this, when n is 0, I'm going to get x. Then I'm going to get x squared over 2. Then I'm going to get x cubed over 3. And I'm going to get x cubed, x to the 4th over 4. And the only thing I realized that I did is I have a mistake here because it is negative of that. There we go. That is the power series. Something is wrong with that. Oh no, that's fine. It is absolutely perfect. Okay, we are going to switch gears and do something different. All right, can everybody see this PowerPoint?
Yes.
All righty. Fantastic. All right, I told you I'd have something for you guys to work on today. And so here it is. All right, so what you are going to do is I'm going to give you 15 series. And with these 15 series, you are going to tell me which test would you use, and if you use a test, you would also need to then say if there is an additional test that you would need to use in order to do this. Okay, here we go. So If it looks like a certain kind of series, then put that there. If there's another way of solving it, all right, then another series test that could be used, use it. If you have to do a limit comparison test to another test, you need to write them both. If you have to do a direct comparison to another test, you have to write direct comparison and the test that you're also comparing it to. All right, so this is number one. So for many of these, you may have more than one test. Okay, any questions?
So are we just saying, telling you which ones we think it is?
Oh, you're writing these down.
Oh, okay, okay. This
Yeah,
is one
you're
picture.
writing these down because it's a lot of, it's actually 15 of them, and I want you to go back and check your score when you're done. Okay. All right, number two. Any questions? Number three. If you need more time, type it in the chat. All righty, number four. If it looks like something you recognize, or you can maneuver it or massage it to make it look like something, then you should do it. Can I go on to number five? Or are you still doing it? Okay, number five. Number six. This is a great way to test yourself too. This is an easy one. Number six is a real easy one. Okay, number seven. All right, number 8. I did number 7 in class. I hope you remember it. Can I go on? Please, somebody type in the chat and let me know y'all are here. I can't even tell. Thank you.
I'm here.
All righty. Thank you. Thank you. Are you doing this?
Yeah, I'm writing them down.
All righty. Good. Here's number 8. See what it looks like. Does it look like anything you recognize? Okay, that's the only way we're going to do this. Number, uh-oh. Uh-oh. It won't move. Let me think why it won't move. Okay, there we go. All right, now it's moving. Number 9. Number 9 should be screaming at you. Use me. The test should be screaming at you. And actually, believe it or not, there's several tests that can be used for number 9. So I'll give you a little bit of time to think about that. Okay, let's move on to number 10. Number 10. Okay. I did one like number 10 in class also. All right, here comes number 11. I did one like number 11 in class. I actually kind of did something like each one of these, actually. All right, any questions about number 11? Can I continue or are you still writing? All right, going on. Hello? Going on to number 12. Okay, number 13. Questions? Number 13 is tricky, but it's actually a very easy one with many, many tests. Many tests. 14. Okay. Last one, 15. And I am going to post this presentation, so if you want to go back through it and look at it, you can. Okay. Plus the video will be posted, so you can look at it on the video or the presentation all by itself. All right, any questions? Any questions? Okay, now you don't have to score it now, but you can score it later. Okay, this is how you're going to score it. You're going to give yourself 2 points for every test that you got correct. So if it, that's self-explanatory. 2 points for every test you get correct. Then you are going to subtract a half a point if you forgot a test. So if it was 3 tests and you only identified 1, you will subtract a half a point for each test you forgot or you did not think of. Okay. Then again, your last thing is if you identified a test and it can't be used. All right, so that test cannot be used. You're going to subtract 1 point from your score. Now, I don't expect you to score this now. You don't have to even score it if you don't feel like it. I'm just giving you a quantitative value of how to do it. 2 points for each test identified, subtract a half a point if you missed a test, and minus a point for any test that you put that doesn't belong. Okay, any questions? All right, somebody give me some ideas for this test.
We use geometric on this one.
Okay, I heard a couple things. PJ, Prentice, would you say?
Geometric.
Geometric series, yes. Anything else? That's
Alternating.
alternating series test. Awesome. Anybody else?
Geometric.
Yep.
I have a question.
Yes.
Do you have the letters next to them? Because I wrote the letters rather than writing the full test.
Oh, I'm going to show you the answer in a minute.
Oh, okay.
Yep. I'm just trying to get some participation to see what people put. Anything else other than GM? There's some other tests that can be used on this. Nobody else?
Oh, wow.
Wow. Okay, it is a geometric series. Okay. It's also an alternating series, so you can do that as well. Because it's an alternating series, you can do the test of absolute convergence and the test for conditional convergence. This is very nicely done with the ratio or the root test. But it is, remember, the ratio and the root test were derived from the geometric series. So the fact that this is a geometric series, I can use the ratio and the root test. Okay. So you get 2 points for whatever you put down, but you get minus a half a point for everything you forgot. And you lose a whole point if you wrote telescoping P-series, nth-term test, interval test, direct comparison, or limit. Okay, Prentice,
So if I only got 2 of them, that means I basically just lose all the points I got.
Yeah, he basically lost. 'Cause that was me too.
really?
Yeah.
Okay, so here's the point of this. This is to make sure you, so you will not forget it again, will you? Okay. I didn't realize a half a point for forgetting something is pretty hefty when I made this. Okay. Anybody?
Ratio.
Ratio test. Anything
Test.
else?
Oh, I got it right.
Yeah, you really can't do anything else with that but the ratio test. And with the ratio test, you will show that this diverges. Okay. All right. Somebody want to give me some ideas? If that 5 was not there at the bottom, what would it look like?
P-series.
Good, look like a P-series. Okay, but it's not a P-series, but I can compare it to a P-series, right?
Yeah.
So
So it'll also be a comparison.
You can use the direct comparison test and you can use the limit comparison test for this one.
So if we like if we take the 5 away, like if we see something like that on the exam, we can like determine that and know that it's a comparison test.
Right, because ignore the 5 at the top. Don't worry about that. But the fact that n cubed plus 5 looks like when n gets really big, it looks like n cubed. That means I can compare this to 1 over n cubed or 5 over n cubed. And because n cubed plus 5 is bigger than n cubed, it can work with the direct comparison test as well.
Okay.
Okay.
So we don't have to compare it, right? It's just what we can use.
Oh,
with
this one, you have to use one of these 2 tests. You have to use the direct comparison test or the limit comparison test, and you are going to compare.
Because of the 5.
You are, say that again?
We have to compare it because it's adding 5. If it was just n cubed, then we wouldn't have to.
Exactly. If it was just n cubed,
Okay.
you could write P series and be done. But because it's n cubed plus 5, you got to do a limit comparison or a direct comparison, and you are comparing it to a P series.
Okay.
So you're either going to use the direct comparison test and the P series, or you're going to use the limit comparison test and the P series. Okay, any questions? Okay. What does this look like? Suppose that plus 1 was not there.
Oh, that's
It would be 2 over 5 to the n, and what is that?
Is that ratio?
I can use the ratio test on this. I can use the root test on
Use
this. I can compare this to a geometric series.
Would you use direct comparison or?
It would have to be limit. Because you're not making this directly smaller than something else. But in the limit, it looks the same. Okay, Any questions? Lots of times when you have powers to the n, a lot of times the ratio test or the root test is very helpful. Or you can compare this to the geometric series. So you could do the ratio test by itself, the root test by itself, or you could do the limit comparison test where you're comparing it to a geometric series. How about this one?
Could we use a root test on this one?
Okay, actually, the root test and the ratio test will not work on this one.
Alternating.
Okay, so the root test and the ratio test do not work on P series. Definitely alternating series. So when you have alternating series, you have the test for absolute convergence and the test for conditional convergence come along with it. This is, if the -1 to the n wasn't there, what would it look like?
That's gonna hurt them.
P series.
Good. All right, so you're going to use the alternating series test. But if you do the test for absolute convergence, you're going to be comparing it. You're going to be using the P series to get your result. So you get these four.
Just because they like.
Wait, what were the other two? I'm sorry. Okay, I got it.
This one's ratio, right?
Yep. This one has more answers than you think.
Could you use the root test?
Yes.
Could we use the alternating series?
Okay, it's not alternating. I don't have a -1 to the n. So I can't use the alternating series test.
Oh, could we also use P series? No.
No.
Integral test.
Yes. The integral test, the ratio test, and the root test.
Was when we had E, was the integral test the only one we used?
I did this in class and I used the integral test. But you can
Right,
do the
but,
ratio or the root.
Okay.
The root test.
I cannot use the root test on this. I would have the nth root of this square root, and I don't know what that is. If that -2 wasn't there, what would it look like?
P series? No, because you have the square root. Never mind.
If the -2 were not there, what would it look like?
E series?
It would be a P series, where P is equal to what?
3. Well,
3.
square root of
The square root is raised to the 1/2 power. So this looks like a P series with P equal to 3/2. So I would use the limit comparison test to the P series, 1/n to the 3/2. Is that going to converge or diverge?
into 3. Oh, it's gonna converge
It's going
because
to converge because P is greater than 1. This one also has more tests than you think, but I would expect that you would use this one main test to do it. What would be the one main test? This is expanded into partial fractions. So what would be the one main test?
Telescoping?
Telescoping series. Okay. I know you're saying, whoa, where did all those come from? Okay. Right now, it's a telescoping series, and that would give you the sum. But if you found a common denominator, you would get n plus 3 over n plus 3 minus n plus 2. So you would get 1 over n plus 2 times n plus 3. So you could use a P series because this looks like 1 over n plus 2 times n plus 3, which looks like 1 over n squared. So you could compare this to a P series. You can do a direct comparison to a P series. You could do a limit comparison to a P series, but the only one that will give you the actual sum of the series is the telescoping. I did one like this in class. Except I think I used the sign.
could you use P series or no?
You are going to use the P series for this. That is correct. But what's the main test you're going to have to use first? You're going to have to put it in absolute values, because the cosine of n pi goes back and forth between -1 and 1. So if you limit it by doing an absolute value, then after you get the absolute value, you can come do a limit comparison to a P series. One test should jump out at you already. Alternating series. So with alternating series, when I take the absolute value to find the absolute convergence, I'm going to get 1 over n to the 3/2 again. So,
P series.
And you can integrate that. Once you find the absolute value of it, you can do the integral of it. You can do the P series. You can use limit comparison test. How about this one?
Sure about that one.
Okay, this one I can use the integral test. Did I just do this one? Oh, I went
That's
back.
number 11.
I went backwards. Okay, there we go. I can do the integral test where u is equal to the log of n. Mhm. I can do a direct comparison test because this integral is greater than the integral 1 over n. The log of n is always bigger than 1 as n gets large. So therefore, this is bigger than 1 over n. So you can do the direct comparison test or a limit comparison test for this. And you'll show that it diverges. Okay. 13, any ideas?
And it was basically, and then once I wake up, I put, yeah, so I've been up here.
That is a geometric series. That is 1 over pi to the n. I can also use the integral test, the ratio test, and the root test. What test can I use on this? What's the limit as n goes to infinity of n over 2n plus 1?
Infinity over infinity.
And then take the derivative. L'Hopital's rule.
Yeah.
What do you get?
Oh, just 1 over 2.
Good. That limit is a half. It is not equal to 0. That thing diverges by the nth term test of divergence. And this last one, what can I do with that? If the denominator,
You factor.
okay, no, we don't want to do that. If the denominator did not have a 3 or 4, what would it look like?
N squared,
Good, which is a
P series.
good. Okay, so we can do a limit comparison or a direct comparison to a P series, or we can recognize that if we take it and split it up into partial fractions, it's a power series. I'm sorry, a telescoping series. I don't know why I said that. It is a telescoping series. Okay. Get the score. We're good. Okay, any questions?
Wait, so what are those examples? If we use one of those tests, we can find the answer, or would it have to be multiple?
Say that again, if we,
So like for all those examples, if we use one of those tests, we can find the answer, or like would it have to be multiple?
oh, no,
What
no,
happened?
no, you can use, so some of them are multiple, meaning if you use the limit comparison test or the direct comparison test, you're comparing it to something else. So you have to include the other thing you're comparing it to. So if I do the limit comparison test, I'm comparing it to a P series. I have to know the P series converges or diverges.
Okay.
But if I'm doing a geometric series test, that's it. I don't have to do anything. That's a single test all by itself. Telescoping series all by itself. P series all by itself. Nth term test of divergence all by itself. Integral test all by itself. Okay, ratio test and root tests all by themselves. The ones that that require you to compare it to something else are the direct comparison, the limit comparison, alternating series, test of absolute convergence, and test of conditional. They will usually require you to look at yet another series to see if it converges. Good question, Rodney. Okay, that's it for today. That's it for this week. I will see you guys on Monday.
Weekend.